Thank you all for coming. This is a joint work with Angelia Nedich and Olshevsky. And you can find a more detailed explanation of what I'm going to present today here in the full version of this talk, which is on a paper on scientific reports, which is open to the public. So I'm going to start by presenting 4 recent applications of network systems as a motivation of why do we need to understand the behavior and the dynamics of belief systems. So I'm presenting here 4 applications. First one of them are sensor networks for agriculture, where in this case you have a bunch of networks that are deployed on the field that are constantly measuring different variables in the soil to make optimal decisions about whether they should irrigate more water or not on the field. And you might see that this seems like a strange applications, but now if you imagine that instead of sensors, you have people interacting with on a social network, exchanging information to make an optimal decision, you start to see some similarities between these 2 systems. And moreover, you can imagine some other applications to security when you have a network of cameras that they want to make decisions in a joint collaborative manner using information from each other. And of course, recent applications for machine learning where the data might not be able to held on a single location and you sort of have different servers connected to the network interacting with each other. So one important issue here is that all these systems that are presented have a common set of characteristics and a common set of challenges. First, the characteristics, they are composed by many units. I will call them agents in this talk. These agents are connected over a network and they have interactions between cyber and physical parts in the sense that not only computational systems, but also systems that are measuring physical variables as well. And they also have different set of challenges with them. Here I present the 3 most important ones that are related to decentralization, the ability to make distributed computations, scalability, which is the price of decentralization, and optimality, which is related to efficiency and performance. So the object of study today is that we're going to imagine to have a network of agents. In this case, I'm drawing them as people, and they are interacting over a network. So the network here is represented as these green lines that connect people with each other, in the sense that if 2 people are connected with each other, they're sharing their opinions about certain topics. And you can see here on the right that maybe a person has different opinions on different topics. So ideally, they will share their opinions on the network, and they try to we would like to understand if the network will agree on a topic or not. You can imagine people having certain opinion on whether they like coffee or not, and you would like to understand if a group of people talking about coffee will agree upon whether coffee is good or bad. So the abstraction model that we're going to approach here is as follows. So we're going to assume the opinion of a person on a topic is represented as a number. And this number could be between 0 and 1. You can imagine if 0 represents that this person strongly agree with the statement, so they like coffee, and 1 represents that they strongly disagree with this topic, so they do not like coffee. And the way we're going to propose, so in this image here, we'll have 4 people, each one of them having their individual opinion about the certain topic. And the way the dynamics goes is that, let's say, person 1 here's the opinion of persons 2, 3, and 4 because somehow they interacted with this person. And this person now has in its mind the opinion, not only his opinion, but the opinion of person 2, person 3, and person 4. And ideally, person 1 will be wanting to build a new opinion based on this new information that he got. And the way we're going to model this is as this weighted information, in the sense that the new opinion at time k plus 1 of person 1 is going to be a weighted average of the information that he has in store and the information that person 2, 3, and 4 share. And in this case, I want to point out that this operation is a linear combination, in the sense the opinion at time k plus 1 is going to be a weighted average of the information from person 1, 2, 3, and 4. And A is a set of weights, in the sense that a weight Aij represents how agent I assigns the weight that agent I assigns to agent J. And we're just going to assume that the total weight should add up to 1. So the new opinions are formed, or the opinion dynamics are formed or are assumed to be formed as some weighted average of the opinions it receives from the neighbors it is connected to. So under this model, let's say we have we would like to understand the behavior of these systems in the sense that whether the systems reach this system is stable or not. Will they reach a consensus on their opinions? How long it's going to take? But so these opinion dynamics models have been studied from a long time, but now we are interested in different types of models, which are logic constraints. So what happens if the things or the topics themselves are connected over a network? So you can imagine that the opinion about certain topics affects their opinions on another topic. So now you have two things. On one side, you have the social network, which directly explains how people interact with each other. But inside our brains, we might have what is called a logic constraints network, which represents how different topics are connected to each other, how one topic influences our opinion on a different topic. And this is the main object study for this paper. We would like to understand the dynamics of systems where not only we have a social network, but we have also a network of logic constraints. And the way to do that is that we not only gonna have a network of a social network itself, which is represented by a graph G, but we also have another network T, which is called the network of logic constraints. So remember the matrix of weights Aij represents the weight that agent I pose on the information coming from agent J. So now we also have a matrix C, which represents the weight that a topic U takes from a topic V. So how topic V influences their opinion on a topic U. And moreover, we're gonna have that, so our opinions are not a single value X, but it's a value that depends on a topic U. So in this case, this type of notation represents that the opinion that agent I has about a topic U on at a time K. So Fredkin, Perskunikov, and Parsegov introduced this concept of logic constraints, and they propose a model on how the opinion dynamics evolve for this type of systems. And the way they describe the systems is in a three-part. So initially, you can imagine that you have a system where the opinion on a topic U is built as the weighted average on the opinions on different topics V that this agent has. As a second step, you have that as a second step, you can imagine that the new opinion about a topic U is formed as a weighted average of that topic on the agents he's talking to, so the social network part. And a third part, you can see some form of stubbornness modeling, where your final opinion in the next step is going to be a weighted average between the initial opinion about that topic and the opinion you built in the previous iteration. So in these three steps, you have first logic constraints, second social networks, and third initial beliefs influence. And for this, we can see a small example here. So we have a network of 4 agents on a social network and a network of 3 topics. So in this case, we have a cycle graph of 4 agents talking to each other and a network of 2 topics, in the sense that topic 3 influences topic 2 influences topic 1. And when these 2 networks interact with each other, what happens is that a new network appears, which is more larger. And how this network looks like, it's modeled at this matrix P, in the sense that it's a larger network whose adjacency matrix is explained as a function of the lambda parameter of the initial beliefs, the A matrix of the network, and the C matrix of the logic constraints. So there's been some results on whether this system converges or not. In particular, Fredkin et al. Showed in 2016 an algebraic structure of showing whether the system will converge or not. And at the end, you need to solve or find a solution for this system of equations in order to find whether the system will reach equilibrium or not. And in this talk, we provide graph-theoretic answers, so answers based on combinatorial approaches to the 3 main questions. First, when does a belief system converges? Second, how how long does it take to converge? And third, what does it converge to? So for this talk, we're going to focus only on the first two steps. So when does a belief system converges? So convergence is a question of existence of a limit. So we have a dynamics on this P matrix. So whether the powers of this P matrix will exist in the limit. And we have an auxiliary result from Jackson 2008 that says that a system like this will converge if and only if every closed, strongly connected component of this graph P is aperiodic. So recall that a strongly connected component are clusters of nodes inside the network that can be reached from each other, and it has only input nodes in links to that cluster itself. So here's our main results. So our main result says that the process in equation 2 converges to an equilibrium if and only if every closed, strongly connected component of the graph P of logic constraints is non-bipartite, and every closed, strongly connected component of the graph G is oblivious. By oblivious agents is non-bipartite. So we have provided here a graph-theoretic condition that guarantees that if this holds, the system will converge. That is, that the network of agents will reach an equilibrium to a point, so that all the agents will reach a consensus. But what is a more interesting question here is how long does it take to reach this point? So assuming that the system reach an equilibrium, reach consensus, how long does it take? And the way we're going to measure this is that this parameter T of epsilon, which is the time, the number of iterations required for the system to be epsilon away from the final point in terms of total variation distance. And the way we're going to approach this question is from a combinatorial perspective in the sense of analyzing mixing time of Markov chains. So we go directly to our result and says that assuming that the matrix G has no bipartite closed strongly connected components, and defining these two parameters L and H, where L is maximum coupling time among all closed strongly connected components, and H is the maximum absorbing time, then we can provide exactly the number K such that if the number of iterations is bigger than this number, then the system is going to be epsilon away from the final point. So we can provide or characterize explicitly how many iterations this system requires to be epsilon away from the final point. So this sort of says first shows that the convergence is exponential, but also provides how many iterations. So we can provide explicit non-asymptotic bounds for this. But the interesting part was, okay, how does L and H relates to convergence properties? And here I show in a very huge table that is inside the paper that for different network topologies provides explicit results on convergence time. So you can imagine here, if the network of edges is a complete graph and a logic constraint is a directed graph, then the maximum expected convergence time is M. And in here I have different results. So we can imagine, for example, let's focus on a couple of them. So let's say if the network of agents is a barbell graph and the network of logic constraints is a star graph, then this table shows that the number of iterations required is the maximum between number of agents cubed and number of topics M. And you can imagine now that depending on the network topology, you will have different convergence rates. So for graphs that look like a barbell, like shown here, this convergence time is M squared. For graphs that looks like a tree, is linear, so convergence depends on M. And then depending on the specific topology of the graph, we can have different convergence results for these type of systems. And here I'm showing a couple of numerical results that show that our expected or the bounds or the behavior described by our theory matches exactly what we will obtain from numerical simulation. So in the first case, we show how the number of agents on a cycle graph affects the convergence time. Second case, we show how the truth statements, a number of truth statements affects the convergence time, and then convergence rate, which is shown exponentially in the third image. We can exploit these results on numerical analysis on real networks. So in here, we exploit 4 real networks related to Wikipedia networks, the network of archive collaborations, and the Facebook network. And we show again that our theoretical results describe exactly the behavior of this type of dynamical systems or opinion dynamics over the network. Again, I want to invite everybody to look into more detailed analysis and explanations of these models on the full paper in Scientific Reports. And there is a couple of open questions yet related to understanding what happens if the networks change with time, how can we model diversity in the logic constraints, how can we use sparse communications, and how can we induce noisy communications as well. And with this, I will end and thank you all for listening to this talk.